Welcome back, Math Model students. This is Mr. Marquetta, and today I'm here to talk to you about Chapter 3.2 and Chapter 3.3 and Chapter 3.4. The first PowerPoint that you see here is on the first two sections, and then the second PowerPoint we're going to go over today in class is on Section 3.4, and also there are important details about exam number 2 in that one. We talked about that a little bit already in class, so I'm going to just leave that there. And then if you want to know those details, you can always go and look at it in the PowerPoint document in eCampus. But I'd like to leave that out of our video recording so that this lesson can be shared with other classes. Today, we're going to do Chapters 3.2, which is Linear Function Summary. And then we're going to do Chapter 3.3, which is Modeling Data with Linear Functions. Chapter 3.2 is going to feel like a review of high school algebra. Chapter 3.3, we're going to start talking about how to model data using technology. So in our textbook, let's start with this important key idea. These are ideas that you already knew. In fact, we did talk about this last time we got together when we studied Chapter 3.1. Remember the circus tent, all the different geometry concepts that have to do with slope. You see here that we can think of the slope m as the change in y over the change in x, or the function adjustment over the variable adjustment. And then since that is a sound equation, you can move the equation and manipulate it to solve it for other parts. For example, it turns out the change in x is equal to m times the change in y, and the change in y is equal to m times the change in x. This will come in handy when you're trying to answer specific obscure questions about measurements in a geometric figure, and knowing those connections with the slope can help us. That's primarily what Chapter 3.1 was about more than anything else. Here in Chapter 3.2, we're going to review a little bit more of the ideas associated with linear functions, primarily the slope and intercept. And like I said, this is something that you probably saw back in the 9th grade and probably again in the 11th grade in Algebra 2. If you ever took pre-calc, they go over this as well because it is the foundation of functions. First, let's talk about the general concept of the formula of a linear function. A linear function always has an initial value. In other words, when x equals 0, what is y? At the very beginning of the story, what is the value of the function? The initial value is also known as the y-intercept, or b, because when you graph it, geometrically, it appears to be the place where your function crosses the y-axis. At the y-axis, all the points on that y-axis have a point that is, the first one is going to be 0, and then the second one is going to be some number. On the x-axis, the x value is always 0. So it's a matter of where it crosses the x-axis that indicates where it actually does begin. If you can interpret it to be the slope times x plus the initial value, instead of just y equals mx plus b and keep thinking of it that way, then all of these questions that have practical applications kind of make sense, and you can employ them you can employ these different formulas to get answers. So what else do we need to know about a linear function? Well, like we said, it's y equals mx plus b. Also, the graph is a straight line. Likewise, the slope is constant, and it's the same as the slope of its graph. So you could connect the slope to the picture and to the function as well. The vertical intercept of the graph corresponds to b, and it is the place where x is 0. And likewise, the horizontal intercept is the place where y is 0. So how do we get the equation of a linear function? Well, usually what will happen is they'll give you a couple of things and one thing will be missing, and then you'll have to go figure out what that one thing is. And then after you do that, put them carefully into the template, into the structure of y equals mx plus b. There are other important formulas that come into play that you might be able to use. If you remember from Algebra 1, there is the point slope formula. You might want to use that. Standard form, but you don't really use that. That's more something to present. But that point slope formula can be avoided if you think about solving for b in different ways. And those of you who are good at this stuff, you know what I'm talking about. But we're going to try to show you all the different ways. That way you have a solid grasp of the idea with many different perspectives. Let's talk about here how to get the equation. First, if you know the slope and the initial value, it's a piece of cake. You just put it right into the formula. So hopefully in a perfect world, the word problem says the first number was this, the slope is that. And so what is the function? And it's easy to just piece it together using the formula, plug everything in where it goes. Notice in the formula, y and x are there. Something that I've noticed working with high school students is it's easy to swap out the wrong X or the wrong Y or something. But remember, you'd like your final answer to have X and Y in it. So if you can keep it in the back of your head when you're writing equations of lines, that kind of gives you a little bit of a background, like, or of a support system that way. For number 2, it says, if you know the slope and one data point, put the slope and data point together into this equation and solve it for the initial value. Now, what they're trying to say there, friends, is if you know a point, say you know that the point is 2, 5, and you also know the slope. If you're in a position like that, you're already kind of halfway there, because if you take that point 2, 5 and put the 2 here where the X is, and put the 5 here where the Y is, and then go and put the slope in, what they told you what the slope was, put that right here and solve it, what will happen is right here, the initial value, which if you remember from your formula is just B anyway, you'll be able to solve for a B and get an answer. Now, remember, like I said, you want your final answer to have X and Y in it, right? Now, that's why this is just a step towards getting your answer. You're substituting in the point that you were given into X and Y here, and you're substituting the slope in just in an effort only to find B, the initial value. Once you found the initial value, say it's 3, whatever it is, take that initial value 3 and take the slope they told you in the beginning of the question, and now go back to step 1 and complete the way that you saw, right? Y equals mx plus b, y equals whatever the slope was, x plus 3, and then you're through, okay? So we have 2 cases so far. The first case is, here's the slope, here's the intercept, what's the function? That's easy, plug it in. The second step is, here's a slope and here's a point. When they give you that, what you do is you substitute in the point into X and Y, you substitute the slope in, and then you get B, or the initial value. Then you take that answer you just got along with the slope that was given and go back to step 1 and assemble the function, all right? For part 3, instead of giving you the slope, sometimes what they'll do is they'll just give you 2 points. And you remember this from Algebra 1. What is the equation of the line through the points 3, 1 and -5, 6? The same kind of question. Instead of giving you the slope, we're giving you two points. But I think you know, if we've given you 2 points and we promise you that it's a linear function, then we are inherently telling you the slope. You just have to go calculate it using the formula. So the first step would be, take those 2 points I just gave you and go do the slope, find the slope. Then you can use either of the 2 points and the slope to go through step 2. Remember, if you can use either of the 2 points, use the easiest one you have. If one of the points is 5, 7 and the other one is -3, -6, use the positive ones. If one of the points is 3, 7 and the other one is 3.09 and 5, 22, use the first one. In other words, be nice to yourself and use the easy one, because since it doesn't matter which one you use, why use the one that has fractions or decimals? Why use the one with negatives? Make it easy on yourself. So just as a brief review for number 3, if you get 2 points and you're asked to find the equation of a straight line, step 1, find the slope. After you found the slope using those 2 points, remember that number and then go and look at the 2 points. Which of the 2 points is easier numbers to play around with? Select that 1 point out of the 2 and then go back to step 2, which is work on finding the intercept. Take the point and plug it into X and Y in my red rectangles. Take the slope we just found and put it in my blue rectangle and find B. When you're through and you have B, now you can go and find the slope and take that B you just found and go to step 1 and assemble the equation of the line by popping into the slope and the initial value. Remember to keep X and Y in place. Now, my friends, I hope that was a good explanation. I'm going to give you a couple of examples now of how you can use those ideas to answer questions. Remember, you did this already back in Algebra 1 with simple numbers. We're going to do them now with uncomfortable numbers because this is math models. So it's going to be measurements that are real world kinds of measurements. So they might be in the hundreds and thousands if they're dollar amounts. They might be decimals if it's microbiology and such. But the whole idea and the concept still holds that this is how you'd come up with the function if it's linear based on certain specific criteria. So please, my friends, keep on coming back to this slide. Keep on coming back here and looking at this one, or go in your textbook and look at KID 3.4 over and over again, because it's great advice about how to handle it when you have the slope and the intercept given straight out, when you have a point and a slope given, and when you have just 2 points. It's all right here how you're supposed to do it. All right. So let's jump in with an example. Oh, well, before we do an example, there is one other little key idea. Let's read through that. When data are linear, a data table for y with evenly spaced values for x can be modeled with a linear function if it shows a constant change in y. If it does not show a constant change, then you cannot model it exactly by a linear function. So take a look at our data here. This is about t in seconds, and v is the feet per second, right? And we're trying to figure out if there is a linear connection here and what the function would be. Notice that at first, I do have an initial value. I know it's an initial value because the x value is 0 there. Make that red instead. A little thicker too. So looking at your table, seeing that you have 0, 0, the fact that you have a number that has 0 in the front implies that the second number is b. So let me just kind of make a special note here. Because this is 0, this is going to be b. So I'm going to put a b right there. Notice that over here in the format, it is b, is 0 over there. Next, let's see if we can figure out what the slope is or if there is a constant change. So what's happening is we have, you'll notice right here, these are all going up in perfect increments of 1 each time. The y values, if you look closely, you'll notice are also going up in perfect increments of 32 each time, very carefully, but they are 32, 64, 96, etc. Those numbers are nice and perfectly 32s. To make an extra assertion, you could go on and check out the average rate of change table associated with this function and think about what happens from 0 to 1. The change was 32. What happened from 1 to 2? The change was 32. What happened from 3 to 4? And what I mean is I'm looking right here at these numbers. What happened there? The change there was 32. Again, 32, 32. And we talked about this when we were doing chapter 3.1, how if you look at your data and you see a regular repetition of the same increment or the same change, then that is something you can rely on as linear. That means that it's linear. And if it's linear, then we can follow all the rules that we saw in the last key idea 3.4, which is the idea that the initial value is b and the slope is constant, and it follows the model y equals mx plus b. So, for example, this particular case, since I have shown that it is linear with an average rate of change table, I can assume that the slope is that rate of change. 32 is the slope. There it is. And remember, it's y equals mx plus b, but here this is about physics, so it's v equals mt plus b, And so just make sure that you include, not to mention, make sure if it's capital, you keep it capital. You know how WebAssign can be like that. Just make sure you're following their variables very closely. And this is the answer we're expecting for this kind of data. So you should be able to A, determine if a set of data are linear. And then B, if they are linear, you should be able to write the function of it. And that is write the function notation of what it would be. And that really is what our primary focus is, friends, today here. All right. All right, so just to reiterate once more, as you can see, I have some circles here in this slide to make it really clear. The idea is that constant change of 32 over and over again, since it's constant, is 32. And notice that since I have a value where x is 0, whatever that y value is, that's going to be the b, like we said. All right, let's go through an example now. I'm going to read this out loud, and I want you guys to try to follow it with me, okay? In this hypothetical experiment, a political analyst compiled the data of the number of registered voters in Payne County, Oklahoma, each year from 2011 to 2016 for each of the following possible data tables that the analyst might have obtained. Determine whether the data can be modeled with a linear function. And if so, find such a formula to predict the number of registered voters in Payne County in the year 2018. Okay, so can this be? Can it? Let's see. Well, first of all, I want to direct your attention to the table number 1. And in table number 1, first thing I would like to do to table number 1 is change around the years. Let's talk about how X is going to be the number of years since 2011. That would make it, instead of 2011, 2012, 2013, 2014, make it 1, 2, 3, 4, 5, which is much easier to deal with. As you can see in the beginning there, and by the way, friends, this is where I'm looking right now, right? As you can see, the numbers here are the same as just what you saw. If we want, we can now analyze all of the changes and talk about what the average rate of change is. And you'll notice if I go from here to here and subtract, I get this figure. I'm going to color code this to make it clear. If I go from here to here, I'm going to get this number when I subtract. If I go from here to here, I'm getting this number when I subtract, and so on and so forth. If I go from here to here and subtract, it goes here. Very small, 16. Last but not least, if I do these two, it will give me this. Now I ask you, are they all the same rate of change? The answer is no. The rate of change is changing variably, and the change in n is different each and every single time. That means this is not linear data. So the answer is no. And if the answer is no, then you wouldn't dare to try to model it with a linear function anyway. So the second part of it, which is, if so, predict the formula, it's not. So I guess you don't want me to do that. All right. Next, let's take a look at the second set of data. In the second set of data, again, we're going to align the data such that 2011 represents the starting point. We could say that in words by saying X represents the number of years since 2011, i.e. 0 means 2011, 1 means 2012, and so on. If we think about the subtractions each time, let's think, if we subtract these two, what is the rate of change? It's 462. If we subtract these two, guess what we get? 462. Now, I put these two together as a comparison to make it clear to you guys. This is how you check to see if data are linear. You successively, carefully subtract every pair of numbers and hope to get the same number each time. If you get the same number each time, you may assume it is linear. Furthermore, you may assume that if these numbers, and I'm going to use a rectangle and a yellow highlighter, if you can see that these numbers right here are all perfectly aligned, 0, 1, 2, 3, 4, 5. Then you're allowed to say, well, I guess the slope is 462 for that one. And it's true, the slope is 462 for that one. You might recall that we talked earlier about looking at a table and trying to find a slope. You can do the same thing if they're not perfectly aligned, but if they are like still in a sequence, like 2, 4, 6, 8, 10, 12. In that case, what you do is you would just divide by the difference. And that may or may not come up. But if it does, we'll come back and talk about that. For now, what I want you to remember, friends, is if you do a table of average rates of change, then you expect for all of these numbers to be the same like this. And if they are not the same, then it's not linear. For example, here, this number is not the same as this number, or this number, or this number, or this number. And that's why the first set is not linear, and the second set certainly is linear. Now, if you were asked to figure out what is the actual equation of this function, it's actually really very simple because, like we said, we have already determined that 462 is going to be our slope. And if 462 is our slope, and the initial value of the function is 28,321, well, take a look at our formula. So the table and analyzing it does make it kind of a little bit easier, okay? And you can pick out quick and easy what the slope is if you have a repeating average rate of change. And you can pick out quick and easy what the initial value b is if you have a point that starts at 0 and you can tell what the y is when x is 0, okay? There is one more small thing in here I want to mention. If you were asking about the year 2018, which they say, if so, find a formula. Okay, there it is. And remember, we're using n and d instead of x and y. And then if so, find the formula, there it is. And now what happens in 2018? Well, we have already determined that D is the number of years since 2011. So if you want to know about 2018, then I think I need to find D of 7, right? Because it's since 2011. So what is 2018 minus 2011? And it's 7. So all you got to do then is just take, oops, hold on, sorry. Sorry, friends, hold on just a minute. There we go. All you have to do is just take n of 7 and put it into this formula and find out what you'll get. You could even use Desmos to do that, and you can make a prediction. You could say, well, according to this data, I think that in 2018, there will be 31,555 registered voters. And that is a very sound, fair, appropriate assessment because the data is linear and because time will march on into the future. Okay, so I hope that that's clear. That's the idea of how you look at data to determine if they are linear or not, and then write an equation or function of it, and then use it to make a prediction. Okay. Let's take a look at example 3.7 now. It says Newton's second law of motion shows how force on an object measured in newtons is related to acceleration of the object, measured in meters per second per second. The following experiment might be conducted in order to discover Newton's second law. Objects of various masses, measured in kilograms, were given an acceleration of 5 meters per second, and the associated forces were measured and recorded in the table below. Like I said earlier, friends, you don't have to be a physicist. We just want you to be able to use a math model. That's what this is about. This one is leaning on physics. It might not be your favorite topic, and that's cool, but ultimately here's some data. What's the equation? You know, that's really ultimately what we're asking about anyway. By the way, it's interesting. It's about force and mass, and if that interests you, check it out. But when it's all said and done, it does boil down to the same thing. What is the story of this data? So part one says check differences to show that these data are linear. Not hard to do. We're going to draw an average rate of change table and carefully go from one to the next. I could see that the change here is 1.5. I could see that the change here is 1.5. Once again, the change here is 1.5 and so on. And you can see that's illustrated in all 4 of these boxes. All right. Next, find the slope of the linear model for the data and explain in practical terms what it means. Now, I want you guys to pay close attention to this because this is so very easy to make a mistake with. Remember when we told you that if this repeats, that it is the slope? Well, there was a little small disclaimer in italics and in a very small font over there. There's a very small disclaimer. And that disclaimer is only when it happens to be true that all of these numbers here are in sequence. All of these numbers are in sequence. Remember before I was saying it has to be 1, 2, 3, 4, but it's not. It's 1, 1.3, 1.6. It's still, like I said, a sequence, isn't it? It is a sequence, yes, but it's not a sequence of a perfect 1, 2, 3, 4. So how do we deal with that? What are we supposed to do for that? Well, the way you deal with that is right here. You're going to subtract. If you subtract any of those two, you're going to get 0.3 every single time, no matter which one of those you subtract. And you could also do that subtraction right here if you want. You could have also done it right here. Subtract here. Don't you still get the same subtraction every time? 0.3. So remember that the slope is supposed to be the change in y over the change in x. Here, the change in y is actually going to be 1.5 each time. But the change in x is actually 0.3. So take a look at this arithmetic now. To find the slope in this scenario, after you've written out the average rate of change table and recognize that it is linear because all of those changes are the same, you're sure it's linear. So now how do you find the slope? Well, since they're all the same, at a first glance, you might say, oh, 1.5 is the slope. But remember, the x values are not 1, 2, 3, 4, 5 perfect. So instead, subtract them. What is delta x? Delta x, or the change in x, is 0.3. So I want you to look very closely, friends, right here. And this is a big part of our lesson today. Make sure when you're doing your web assign, as you're going through, when it's time for you to find out what the slope is, if you don't have 1, 2, 3, 4, 5 right here, then you need to subtract and find the change in x and make it your denominator right here. All right. I hope that that helps a little bit. Next, construct a linear model for the data. Okay, we could do that. To do that, first I have to figure out what b is because I do not have a point that starts with 0. In other words, what I'm trying to say is I do not have an example of a point in the beginning, like I usually do, of 0 comma something. It starts with 1, 1 is not good enough. It has to start with 0 to be an initial value. So how can I figure out an initial value? Well, the good news is I do know the slope. And I do have an example of a point there. In fact, I have many, many points. Since this point that I have highlighted in the purple oval, they're both whole numbers, I think it would be smart to use that point. Remember, when you're doing a point slope approach and you have many points to choose from, take the shortest path. 1,5 is much easier than 1.3, 6.5. Try to use the easy way. So that be the case, 1,5 is the point I'm going to use. I know that the slope is going to be 5. And now I can use this idea, y equals mx plus b, and put in an example. F is 5 and f is 5 and m is 1. That's because m is x, right? And x is 1. So we're talking about this point right here. This point is actually 1, 5. Using that point, I can take 1 and put in the position of x or in the position of m here. And then, of course, y or f is the 5. This was a little tricky because mass is m and slope usually is m, but don't let that throw you off. It ultimately is just y equals mx plus b, but the m is there because m is the independent variable this time. And just go through the work and solve, and you will discover that b is 0. So if b is 0, then what that means is b is 0 and m is 5. So if it's y equals mx plus b, you're going to get this as your final solution. F equals 5m, really plus 0. But then what plus 0 means it is what it was. All right. So the last thing that we ask here is, objects of various masses measured in kilograms were given an acceleration of 5 meters per second. Now answer the questions below, and part 4 says, what force does your model show for an object of mass 1.43 kilograms that is accelerating at 5 meters per second? Well, remember that here they're telling you about how this is all based on the idea of being given an acceleration of 5 meters per second. So here they're saying blah, 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 accelerating at 5 meters per second. This 5 has no bearing on the story. It's part of the initial introduction. So you're not going to multiply it by 5 or think about 5 or use 5. And often in the actual wording of the description, they will say something about the $5,000 club. The number 5,000 has nothing to do with it, but it's a number in the context. So critical thinking skills come into play here. And with your reasoning, you have to know that some things are just to be cookie cutter, copied right off from where they were. So given an acceleration of 5 meters per second, I really barely know what that means. This is saying accelerating at 5 meters per second. Again, I barely know what that means. I teach math, not physics, but I'm copying the wording, and the 5 happens to be one of the words. It's not part of the calculation. However, it is true that this certainly is part of the calculation right here. And if the mass is 1.43, then right here where I have m, I'm going to want to put 1.43. And here you could see the arithmetic of figuring out the final solution that you're getting 7.15 newtons. Okay. So this is example 3.7. Here, again, we're only talking about if you have data that are linear, can you find a function for it? And can you make predictions using it? Chapters 3.2 and 3.3 really do ultimately lend themselves back to Algebra 1 and Algebra 2. These topics were covered in algebra, except in algebra, they might not have given you such extreme applications like using Newton's second law and other things like that. For chapter 3.4, though, we are going to talk about something that you may not have seen in algebra, which is linear regression. And that is coming up with the best line if it's not linear. And we're going to do that now using the other PowerPoint slide. But before we do, we're going to take a look at just one more case. Oh, I don't think we're going to look at one more case. That's this slide. Oh, okay, great. Well, let's take a look at the next slides now, okay? And the next slides also can be found right there on your eCampus e-learning. And here's your next lesson, okay? And this is the last part of today's lesson. And once again, thanks so much for your attention. We're going to talk today about linear regression to close our lesson today. Linear regression, first I'd like to talk to you for a minute about the word regression. What does regression mean? Those of you who have ever taken psych We have something in psych called coping mechanisms. One of the most common forms of a coping mechanism is denial. So if you say to somebody, I think you have a problem, and they say, I don't have a problem, that's an example of denial. There's a nice long list of them, and it's a very fascinating psychology topic, coping mechanisms. One of them is repression, which is when you forget something traumatic in your past and it might bubble up and explode later. And then we have something called regression. Regression is not repression. Regression means, and the verb to regress means to go back. Regress means to go backwards. Someone is having a regression coping when they are crying like a baby, because as an adult, I mean, it's not that you shouldn't cry when you're an adult, but you shouldn't stamp your feet, you shouldn't scream when you're an adult and all those things, but those are characteristics of maybe an adolescent. You might hear about a person who is having a midlife crisis going back to activities that were acceptable in adolescence and young adulthood. This is what we mean by regression. And in mathematics, regression holds the same definition. In mathematics, we have points that are scattered because of natural data. If I just asked each of you, what is your age and how many credits do you have at Monmouth University? There's probably some kind of relationship connected to that. There probably is. But it's not a perfect exact relationship that I can always say, well, since this data looked like this, I can promise it will look like that because it is a linear function and it's always the same, because it's not going to be always the same. However, it'll be kind of the same. And that's what linear regression is taking data that aren't exactly linear, but are almost linear, and finding out what the line would be if they were linear, and last, using that line to make a prediction. So everything that we learned in chapters 3.2 and 3.3 still hold, having to do with how to find an initial value, what a slope is, and all those other great things. But before we start answering questions like that about scatter plot data, we have to analyze the data to just see if it's linear-ish. And if it is linear-ish, then we can apply this concept of regression, okay? In human words, that's what regression means, okay? You're finding what it would be if you could make it that. So if you're given a set of points, the regression line is the line that best fits that data. To perform a linear regression means to find the line that fits that best fits that data. Before performing a linear regression, though, first you have to examine that data and determine if it's approximately linear. That can be done with a brief visual analysis through plotting or by making a table of changes. So here are some examples of that. What you're looking at are images from your textbook from the TI-86 calculator, which we're not using. We use Desmos in this course. But if you look at these data, take a look at the first set of data there. It looks like a line, kind of. And if I try to draw a line, I can kind of get a line to go through them, but it doesn't exactly. As you can see, some of them are a little bit more on the line than others. And if I was able to really, really zoom in, it probably doesn't exactly go through each and every line. However, it certainly does appear to be pretty close to going through all of that. And that's just what we mean when we're talking about, is it approximately linear? See how that line over there looks like it just about does go through each of them? It really kind of doesn't in a microscopic way, but it does kind of look like it could pass for a straight line. And since it looks like it could pass for a straight line, it's appropriate to apply a linear regression to it. So what we're going to do is we're going to use Desmos. And when we use Desmos, all we do is simply enter all the data, all the XY points into Desmos. And I'll show you just how to do that. After you're done, you type in a certain specific command, and then it will spit out what the slope and intercept should be for the regression line. In fact, you really don't even have to think very hard. Just type the numbers in, type the thing in, and look at the thing that comes out and write it down. It's actually made so easy that you can almost lose sight of what you're actually doing when you're performing a linear regression in Desmos. So I'm here to try to make that clear for you and show you what really is happening. What's really going on is you're putting in data points. Desmos will show you a plot with dots. And then Desmos will figure out, which is a very long and tedious, difficult process, what exactly the slope and intercept of the line of best fit are. Then when Desmos gives you the slope and the line of best fit, all you have to do is take those two values and include them into the slope intercept formula and put it in the model of the function that we talked about from chapter 3.2. And there you have your line of best fit model. And you can use that now to answer questions. So Entering as many points as possible will optimize the accuracy, meaning if you put in 10 points, that's great. But if you put in 50 points, you're going to get a much stronger line that really better shows the data. If you could put in 1,000, a million, as many points, as many values as you can, the more values you put in, the better that line will be closer to what the idea of regression is. So you can use that regression line to estimate values between values, and you can use it also to approximate far away values. Remember in the last case where we had data up until 2016, and then you used that data to answer what would happen in 2018? That was based on a linear function. If it was not exactly linear, but kind of linear, and then you got the regression line from it, you could use that line to find 2018, and it would be an appropriate prediction. So now let's talk about Desmos. And today I am going to be looking in Desmos with you and showing you how to do this in Desmos. Okay, approximating models with regression lines. We'll talk about an example that is similar to the example on chapter 3.4, example 3.8. This example, friends, is not in your textbook. It was in a previous edition of your textbook. However, when I first made these PowerPoints, I went and used that, and it still was a really great example. So I kept it in the lesson. You won't see this in chapter 3.4. You'll see it here in our PowerPoint only, unless you buy an old textbook. Here we have something that's similar to the Medicare question, which was in billions per year since 2009. And here we have some data. We have T, which is our time in years since 2009, and we have E, which is our expenditures for those years, and we have figures here. Let's take a look at how we figured out some regression lines for this. So before you find the regression line, take a look to see if the data are linear. You can do this in two different ways. You could do it with a visual analysis or by making a table of changes. Here's what it would look like as a visual analysis. First, you go into Desmos. You would go to the plus sign on the top left like you see there, and then you would click table, and then you would type in these numbers just the way you see them. When you do that, you're going to get a picture, and you could zoom in and out and use the wrench to get a picture, but taking a look at the picture or using the wrench, when you get the picture, do the dots kind of line up or not? Look at them, they kind of do. I would argue this is a great example of a group of scatter plot data that should have a linear regression. All right, let's show now how you would go into Desmos and actually make this work. Okay. Here we are in Desmos. Let's say you're trying to find out right now what the dots look like to see if it's a linear regression model candidate or not. Enter the data. Here's how you enter the data. You go right to the plus sign right here and put a little arrow next to that. Go to the plus sign, and then from the plus sign, you'll get an option, choose table. Here's a table. What data would you like to enter? So I'm going to go and get the data. In the X values, it's 0 through 4. Y values are going to be 498.8. 520.5, 546.1, 569.2, and 586.3. Oops. And I think you could see this only goes from -10 to 10 and from -6 to 6. I mean, we're looking at 498. Let's zoom out. Let's zoom out. A whole lot. Zoom out a real lot. I got to get up to the hundreds. There they are. It may feel like that's good enough, and it kind of is, but still, let's just get a really good picture of it. It looks like my x values are going from 0 to 5. So let me change that in the x in the wrench. I like it go from -1 to 6. I like to go a little behind, a little before. Also, you'll notice that my values only range from 498 to 586. Why don't we make it go from like 450 to 600? And now if you look at that, yeah, that looks like a line. That looks like a nice straight line. Okay, and you're just a little tiny bit off. If you try to draw a line through there, you could see you'll never really make it work. It won't exactly work right. It's tiny bit off. So you're really in an excellent position to perform a linear regression on this data because they are approximately linear, as they would say. Okay, let's go back and look now at our PowerPoint slide. Carrying on from where we were. The other way that you could do this is by making a table of changes. So here's what it would be like if you made a table of changes. If you go from 0 to 1, 1 to 2, 2 to 3, and do our subtractions, remember me drawing these adorable little rectangle, circles? Subtract these and you'll get this number. Now subtract these and you'll get this number. Now subtract these and you'll get the next number. And one more time. Subtract these and you get this number. Now look at those numbers. The differences are 21.7, 25.6, 23.1, and 17.1. Those are your differences. They're pretty close. Arguably, they're pretty close, at least in the scope of in the hundreds, 400s, and 500s, for the change to be only at its most a change of like 17 to 25 is only 7, whereas all these numbers are in the hundreds. Again, you could kind of look at it and say, yeah, it looks like it's linear. But then again, it is really kind of a matter of opinion. Something like this, you could really kind of argue either way or the other. The way to put it in perspective is realize that 25 and 23, 21, they're only 2 or 3 apart each time, and the actual figures are all the way up in the hundreds. So this is approximately linear. The point of this piece here is to show how to prove whether or not something can be considered approximately linear. It's approximately linear if when you graph it, the dots look like they're in a line. Or if when you do an average rate of change table like this, all of the differences are almost the same. They don't have to be exactly the same. If they were exactly the same, you would not need to model it. It would be linear, and you could write the equation of it. All right. So that's the story. See if we can now take that data and come up with some kind of answer for what the line of best fit would be. So after the data are entered into the form, the regression line can be found by entering this important syntax. Now I want you to look very closely with me, friends, at this, the way this is written, and I'm going to highlight it for us as well, because we need to talk about this today. We need to talk about this. Y1, and that is not an equal sign, that is similar to. You can find that if you look on your keyboard where the numbers are across the top, on the far left, to the left of the 1, if you hold Shift and hit that button, it represents an accent, or it represents what's called a tilde. And the tilde is used in Spanish. You can put it over an N, and it makes an N sound like Enya. Or you can use it in geometry to show similar figures. And it does imply similarity. In more advanced mathematics, we use that symbol to mean other things. But here, it does represent similar-ish, meaning approximately. And what you're looking at is the equation of a line that would be the approximate line of best fit for the data that were originally given. So when you have your data in Desmos, the next thing you do after the data are in Desmos is you open up a new cell and you type this funny looking syntax into it. What you're doing is you're saying, okay, Desmos, will you please approximate or do a similar analysis of what X and Y would be based on this data? Because X1 and Y1 are a column of data that I already put in. Can you take that X1 column and that Y1 column and think about what the right line would be for X and Y for that? So what we have then, we would type it in like this, and it would put a line up there for us. And after it puts the line there, it tells you specific values that are associated with the line. The regression line is added to the graph, and they tell you what B is, and they tell you what M is. Look, it's right here. M is going to be this, and B is going to be this. That's why when you're done with Desmos, you're in a position to construct the final answer. Notice that the numbers from Desmos are inserted into the positions of M and X. And also, instead of Y1 and X1, this is a story about expenditures and T time. So it's capital E and lowercase t. And so that's what we would want for something like that. I'd like to show you now in Desmos, when you type it in what it looks like to get that equation of that line of best fit. Let's go back to Desmos. Okay, and in Desmos, I'm looking at the data. And I think you can see I do have my data written there. I'm going to get a new box by clicking right here like so. And in that box, I'm going to put a command. I'm going to say, Desmos, will you please relate the data I just put in, Y1 and X1, in a linear way and tell me what that line would be if I was trying to figure out the line of best fit? Sure, Anthony, here it is. M would be 2.23 and B would be 499.4. They're not telling you flat out what the equation of the line is, but you should know looking at it that this is the slope and this is the intercept, and now you're in a position to follow the rule of y equals mx plus b and type those numbers in for the m and the b and type in the other variables you need for y and x. Okay, I think you can see this is not very hard. It's just a matter of practicing it. And in WebAssign, we have a lot of great questions that are associated with this, and you can keep on practicing them. There's great tutorials and videos there as well to help you out. Now, the regression line can be used to predict projected spending as well. So what happens in 2014? If it turns out that these are in the years since 2009, then we can assume that this is 2009 and this is 2010 and 2011. In other words, just add to it until you get to what you want. So if it's 2014, then I need to know what happens in year 5, right? Because if this is 11, 12, 13, 14, 15, yeah, 2014, we try to find out what happens in 5. The problem is we don't know what happens in 5 because we just genuinely do not know the future. But we do know what has happened in the past. And we can use that data to make a determination about what we predict will happen in 2014. Let's do that now. Let's go back to Desmos. Before I do that, let me show you how it comes out here. What you do is you'd use that original formula, and here it is. And in the place of t, insert a 5 and do a little calculation. If you want, you could just go into Desmos and type it, but I want to show you something in Desmos to make sure we don't make confusing mistakes here. All right. If you're trying to find out what happens with 5, make sure that you don't just put a 5 here. 5 is not going to be here. That's not going to be how you get it. Instead, what you have to do is write in there y equals, and type in the actual formula, 2.37 x plus 499.44. And notice it covers the black line. The red line is covering the black line. Why? Because they're the same line. Now, why did I do that? Because now that I have this here, I can hit the gear and I can change this into a table. I can say, okay, now what happens when I get a 5? There it is. Now, if you don't want to do it that way, you could go back like I showed you, just plug into X 5 and do the work and get it. You'll still get 611.29. But remember, the line that you have here, the black line is the line of best fit. There is not a place for you to do that. Here, we have it, we'd have to rewrite it and put it in and type it in again. So you can do it that way if you like, or you can just figure it out with a pencil. All right. All right, now let's go through another example. And in this one, it's military expenditures, which I think is probably what they change it to, because Medicare expenditures and military expenditures sound very much alike. But again, this is a great example, and I'd like to go through this with you as well so that you have a lot of good reinforcement about how to do linear regression. Okay, let's go through example 3.8 as well. The following table shows the amount M of money in billions of dollars spent by the US on national defense. In the time row, t equals 0 corresponds to 2004. T equals 1 refers to 2005, and so on. So t is in years since 2004. Great. Now plot the data points. Does it appear that it's appropriate and to approximate these data with a straight line? All right, let's go into Desmos and let's see what that looks like now. I'm going to clear everything out of Desmos right now. And then I'm going to click home to get back to the beginning. And since I'm working on trying to find out if data are linear, let me enter some data by pressing the plus. I press plus and I choose table. And the data that I'm looking for from the PowerPoint slide, they're only going from 0 through 4. And you'll see it does default, so keep going. There you go. There's your 0 through 4. Now let's put the values in for y. 455.8, 495.3, 521.8, 551.3, and 616.1. I don't see them, but that's okay because I know they're up in the air. They're in the 400s and 500s. As you can see, it's very similar to the last lesson we just did. So let's zoom out a little bit and get a good picture of them. There they are. And to get a better picture, I can look at the data. And I see the data really goes from 0 to 4 in this case. So let's click the wrench and let's make the data go from maybe -1 to 6 or 5 or something like that. And that's really good enough, but I still want a little bit of a better picture. The lowest is 455, the highest is 616. So let's go from 400 to 700 then. Okay. Does it look linear? It sure does. Is it a little funny looking? Yeah, but it's linear. It does look linear. And remember, you're looking at it very, very, very close up. So I could certainly draw a line through it. I'm not sure where it will go. Probably something like this if I draw it, right? So that be the case. Let's now tell Desmos, but well, one thing at a time. Is it linear or not? Yes, the answer is yes. So now let's take a look back at our slide, okay? So we say, does it appear that they're linear? And when we plot them, we get dots that are in order. Now it says find the equation of the regression line. So if you're gonna find the equation of the regression line and then add that graph to the line on your data plot, Desmos already does that for you. Let's go in and find the equation of the regression line. All you have to do is say in syntax, okay, Desmos, please relate column X1 and column Y1 in a linear way. So I'll write the formula of what linear means. Y1 similar to mx1 plus b. And now I have some answers. I have right here the slope, and I have right here the intercept. That means I can write out the formula. The formula ought to look like this. Y equals 37.66x plus 452.74. That is the equation. And notice when I graph it, it's blue and it just covers it. So you don't have to have that there, but it does help to have that there if you try to do predictions. Next. So we found the regression line. Remember, we want it in m in terms of t, so it is important that we do that correctly. We did have m and b, and we used x and y to get our answers, but remember, it's in terms of m and of t. All right. For part 3, it says, explain in practical terms the meaning of slope and regression model that we found in part 2. To be specific, it is a positive slope, and it is going up. That means there is a positive relationship. Also, you could say things like it's a strong relationship because the dots are kind of close to the line. If the dots weren't that close to the line, you might say it's a weak relationship. The slope being positive tells you that it's a positive relationship. If the slope was negative, i.e. going in a downward motion instead, then you would say it's a negative relationship, meaning the more of x, the less of y, or vice versa. And last but not least, it says now use the regression equation to estimate military spending in the United States in 2009. Well, if this is 2004, and then 05, and 06, 07, 08, right? If these are all the years, right, I guess 09 represents 5. So I think you can see this is the same as the Medicare expenditures. It's the same question again. You know, they made it a little different. But anyway, this is the one that's in your book. And to figure out the answer for what happens in 2009, we're going to substitute t equals 5 in. And that's really easy to do using Desmos. Make a table out of it. And then find out what happens when it's 5. And there's your answer, 641.04. Okay. So here's the formula that we talked about. in terms of M&T. And last but not least, here's the answer. 641.04. But remember, it is in billions. So make sure you say $billion when you're through, or change it into billions by multiplying and moving decimal points. All right. Now, what I have here is an example for you to test your understanding. We are going to end class shortly. So what I'll do is I'll leave this here for you, and I'll also leave for you what the answers are, like so. This is how you would go about doing it. And I want you to make sure that you come back and take a look at this and go through this example and make sure you got it the right way. I just did this for you guys twice. One thing that is important about this one that's got a little bit of an extra mean bonus in it is if you look really closely right here, you'll notice this does not go up in perfect increments. It goes 2, 4, 6, and then we have 7 and 8. Just make sure that you keep that in mind when you put all the dots in, because that if you put 0, 1, 2, 3, 4, 5, it will come out wrong. You have to make sure you're careful with both the X and the Y. And that's something that's the only difference in this one between this and the last one. And I recommend that you definitely give this a shot. And if you're familiar with how that works, then, I think you got the grasp the idea of the lesson. All right. This is the agenda for week number 2. If you're in my Math Models 09 Spring 2022 class, if you're not and you're just watching this for whatever, in a future class, please disregard this part of our PowerPoint. And that's everything I have for you guys here today. And thank you so much for your close attention to my lesson. What I'd like to do now, guys, is stop the lesson, and I'll stop the recording, and then I'll open it up to any questions you might have. Once again, thanks so much for your attention. And WebAssign, the 2 WebAssigns associated with these lessons are now available, and they will not be due until March 20th.